So let's see the proof of the Rees-Fisher theorem. So let Fn be a Cauchy sequence in L1 Rd. So here again I am writing Fn rather than the equivalence classes, because the meaning is quite clear, because we only have equality almost everywhere for the other representatives of the same class. So rather than writing box Fn, we are just writing Fn as any representative in the equivalence class. So if it is a Cauchy sequence in L1, so we have to show that there exists a complex measurable function f which belongs to L1 Rd, such that norm of Fn minus f in the L1 norm goes to 0 as n goes to infinity. So Fn Cauchy is a Cauchy sequence is the same as saying that for all given epsilon greater than 0, there exists a number n epsilon such that the norm of Fn minus Fm is less than or equal to epsilon for all n and m greater than or equal to this number n epsilon. So this is what a Cauchy sequence means in our case. And let me remark here that this does not imply that Fn converges to f pointwise almost everywhere for some measurable function f. So L1 convergence, which means that if you have a Cauchy sequence in the L1 norm, it does not imply that you have pointwise everywhere, almost everywhere convergence. So let me give a counter example to this fact. So let Fn be the indicator function of the following set. So for n greater than or equal to 2 to the power k less than 2 to the power k plus 1, for k greater than 0, we take n minus 2 to the power k over 2 to the power k, and n minus 2 to the power k plus 1 over 2 to the power k. So we take the indicator function for this interval, and we note that these intervals n minus 2 to the power k plus 1 by 2 to the power k, these are all subsets of 0 1. Okay, so for all n greater than or equal to 1, where k is chosen such that n lies between 2 to the power k and 2 to the power k plus 1. So first of all of these sets are within 0 1, and the measure of these sets, these intervals over 2 to the power k, this is simply 1 over 2 to the power k. So as n goes to infinity, the measure of these sets n minus 2 to the power k by 2 to the power k, n minus 2 to the power k plus 1 over 2 to the power k goes to 0, since k also goes to infinity if n goes to infinity. And note that this measure is nothing but the L1 norm of Fn. So this means that the L1 norm of Fn goes to 0, because this is a simple function. So the L1 norm is simply the measure of this interval. So the L1 norm goes to 0, and this implies that we have a Cauchy sequence. This sequence Fn n greater than or equal to 1 is Cauchy, but there exists no function, no measurable function f such that Fn converges to f pointwise almost everywhere. So let's see why this is the case. So first is that for no x in 0 1, Fn x converges to 0 as n goes to infinity. This is because the nature of this sequence of indicator functions is such. So if you take the interval 0 1 and 2 to the power k is less than or equal to n less than 2 to the power k plus 1, then this interval is subdivided into subintervals of length 1 over 2 to the power k. So like this, and then when n is 2 to the power k, this is so let me write it here. So this is chi 2 to the power k, this is f 2 to the power k, and then f 2 to the power k plus 1, then f 2 to the power k plus 2, and so on. And finally, when you have, sorry, here 2 plus 1 plus 2 and so on, and lastly the last sub interval is f 2 to the power k plus 1 minus 1. So you see that when n is between 2 to the power k and 2 to the power k plus 1 in the exponent, we have that the indicator functions moves from one to the next of these sub intervals, and then when n equal to 2 to the power k plus 1, if n equal to 2 to the power k plus 1, then it goes back here with a smaller interval right at the beginning of the interval 0 1. So here this is f 2 to the power k plus 1. So the indicator functions keeps moving from back and forth in the interval 0 1, and this is why it's called the typewriter sequence. Typewriter's sequence. I don't know if you have seen an old typewriter where you had to move back the lever to print again. So it is, this is why it's called the typewriter sequence, and this is why, because of this oscillation back and forth, this is the oscillation of these indicator functions back and forth, we do not have pointwise convergence. So this is just a heuristic argument, but you can always write down an explicit proof. So I'll leave it as an exercise. Write an explicit proof. Write an explicit proof for this fact that Fn x does not converge to 0 for any x. Now the second one is that suppose that Fn converges to some f pointwise almost everywhere, then first of all that f equals 0 outside 0 1, because Fn is 0 outside 0 1, and secondly f lies between 0 and 1 within the interval 0 1. So this is just from the nature of the sequence fn's. Then we see that the norm of fn minus f, the L1 norm, is going to 0 as n tends to infinity, because since fn minus f, now these are both between 0 and 1, so therefore this is bounded above by 1 and it is 0 outside the interval 0 1, so it is bounded by the function, the indicator function of 0 1, and this is an integrable function. This is integrable, absolutely integrable L1 function, and so this implies by the dominated convergence theorem that implies that the norm of fn minus f L1 norm goes to 0. But we have already seen that the norm of fn goes to 0, and since we are in a metric space, it's always Hausdorff, so we cannot have two limits. This implies that f equals 0 almost everywhere, which is a contradiction from the previous part. So we see that even if you have a Cauchy sequence in L1 norm, it does not imply that it converges pointwise everywhere, almost everywhere, to a function f. So now that we have seen this counterexample, let's go back to our proof of the Riesz-Fischer theorem. So we have a Cauchy sequence in the L1 norm. Now, even though we do not have pointwise everywhere, almost everywhere convergence, we still can extract a subsequence which converges pointwise almost everywhere. So this is the idea for the proof. So going back to the proof, of the Riesz-Fischer theorem. So the idea is to extract a subsequence fnk of the sequence fn, which converges fast enough, and what do I mean by fast enough, I will make clear in a while. So which converges fast enough in the L1 norm. So this would imply that there exists a measurable function f such that f and k converges to f pointwise almost everywhere. So this is the idea, and now let's see the details for this idea. So of course fn Cauchy implies that for each k greater than or equal to 1, if we take epsilon to be 2 to the power minus k, then there exists a number small n k such that the norm of fn minus fm is less than or equal to 2 to the power minus k for all n and m greater than or equal to this number nk. So if we choose nk plus 1 such that nk plus 1 is greater than or equal to nk, then we have fn plus nk plus 1 minus fnk, the L1 norm, is bounded above by 2 to the power minus k, and this is the subsequence that we want, and it converges fast enough because now we have on the right hand side an absolutely summable sequence. So Now define fx to be the sum fn1x plus k from 1 to infinity fn k plus 1x minus fn kx fnk. Now this is a telescopic series. And if you look at the partial sums for this series, so for any capital N in N, if we take fn1x plus k equal to 1 to capital N fn k plus 1x minus fn kx, then this is nothing but simply fn capital N plus 1 of x. So which means that fx is the limit as capital N goes to infinity of this partial sum fn n plus 1 x. And so if we prove that this limit exists almost everywhere, then f will be a measurable function for which this subsequence convergence always almost everywhere to f. So if we show that fx is finite for x almost everywhere, then this subsequence fnk converges to fx for almost every x. So this is a pointwise convergence almost everywhere. So we have to show that this is a finite for almost every x. So we claim that f is an L1 function. So this would imply that f is finite almost everywhere, because we have already seen that L1 functions are finite almost everywhere. So to show this, it suffices to show that the modulus of f is less than or equal to g and g belongs to L1. So first of all, the modulus of f is less than or equal to g by construction. So mod f is equal to the modulus of fn1 plus the sum fnk plus 1 minus fnk, k equal to 1 to infinity, and then you can use limit on the triangle inequality. So you will get modulus of fn1 plus the sum k equal to 1 to infinity mod fnk plus 1 minus fnk, and this is nothing but gk. This is the function g, and so modulus of f is bounded above by g. Now to show that g is L1, we consider the L1 norm of g, which is equal to the integral of this function modulus of fn1 plus this sum k equal to 1 to infinity modulus fnk plus 1 minus fnk dm. So this is over Rd, and we have the integral of this function, which is a non-negative function. And now we can use Tonelli's theorem to interchange the sum and the integral. So this implies that this is equal to the integral Rd fn1 plus the sum k equal to 1 to infinity of the integrals over Rd Fn k plus 1 minus Fn k, and this is nothing but the L1 norm of Fn k plus 1 minus Fn k, and each of them is less than or equal to 2 to the power minus k. So therefore this is less than or equal to the L1 norm of Fn1 plus the sum k equal to 1 to infinity 2 to the power minus k, and this is an absolutely this is a summable series, so it's finite. So the L1 norm of G is finite, which means that f is an L1 function, which means that f is finite almost everywhere. So we have shown that f is finite almost everywhere, and so fx is the limit as k tends to infinity of these f and k's. This is pointwise almost everywhere. So this subsequence converges to a measurable function f. Now we have to show that the whole sequence Fn converges in L1 norm to f. So to show that the norm of Fn minus f L1 goes to 0 as n goes to infinity, we first show that the subsequence Fn k also converges to f in the L1 norm as k goes to infinity. So this is nk, f of nk. How do we show this? So let's fix k naught. Then if you take fx minus fn k naught f of x, then this is nothing but modulus of the sum k equal to k naught plus 1 to infinity f n k plus 1 x minus f n k x, and this is of course less than or equal to the sum of all this modulus of all these individual terms f n k plus 1 x minus f n k x, and this is less than or equal to the function g. So we see that f minus f n k is dominated by this function g, and this implies by the DCT, the dominated convergence theorem, shows that the norm of f minus f n k goes to 0 as k goes to infinity. So we have shown that the subsequence converges to the function f in the L1 norm. Now final step, finally we show that the norm of f minus fn L1 goes to 0. So given epsilon greater than 0, we choose a number n epsilon such that the norm of fn minus fm is less than or equal to epsilon by 2 for all n and m greater than or equal to n epsilon. This is by the Cauchy property of the sequence fn. So this is by fn or Cauchy, and now choose nk greater than or equal to n epsilon such that the norm of f minus fn k L1 is also less than or equal to epsilon by 2, and this we can do since the norm of f minus fn k goes to 0 as k goes to infinity. So we can choose our nk greater than or equal to this number n epsilon that we have chosen here, and we get a similar inequality. So finally, if you take the norm of f minus fn, so for any n greater than or equal to n epsilon, we have that f minus fn is less than or equal to, the norm is less than or equal to f minus fn k. So this is the chosen nk L1 plus fnk minus fn L1, and this is less than or equal to epsilon by 2, and also this second term is less than or equal to epsilon by 2 because both these terms are greater than or equal to n epsilon. Both these indices are greater than or equal to n epsilon, for which this holds by the Cauchy criterion. So this is epsilon, and finally we are done, and we have shown that fn converges to f in the L1 norm. So as a corollary of this proof, so this finishes the proof of the Riesz-Fischer theorem, but as a corollary we also obtain the important result that if fn minus f, the L1 norm, goes to 0 as n goes to infinity, then there exists a subsequence fnk such that fnk converges to f pointwise almost everywhere. So we can choose our fnk so that this is a pointwise almost everywhere convergence, and this is always true whether or not fn converges to f pointwise almost everywhere.